Okay, guys, welcome back to the last session on the stage today. After this, you're going to be welcome to the alpha stage for the final session. And also want to maybe inform some of you, maybe just remind the major part of you that we have the legendary Build Stuff after party tonight. Yes, it's I mean, it is legendary because it's probably the most talked about thing in Build Stuff every year. And I've been there only once, and I will never go there again because it was hell to work on Friday morning. So anyway, it was amazing, and I really invite you to go. You can find everything and all the information about the party on buildstuff.com, and it's happening in Vakaris, somewhere there in Vilnius. Please find it, please Google it. Everything is on our website. And this guy without a microphone, now he can't interrupt me, is Ian Cooper, and he is here for almost, I think it's 10 years in a row. Yeah, something like that. So, I mean, he knows what to do, and that's why I will believe in him, and he will do his own Q&A session. I will be working on other stage, and that's it. What you going to talk about?
I'm going to talk about, at least once, so Pat Helland's articles about life beyond distributed transactions.
Whatever that means. So, yeah. For the Pine users as well, you can please inform them about your Twitter handle and all the other contacts. So people on the Pine are always asking about that. And that's it. I'm leaving you, and I'll see you tomorrow after the party. I hope you have a good time. Bye.
Hey, everyone. Thanks for coming. So we're going to talk about some of Pat Helland's stuff. That's my Twitter handle, iCooper. My DMs are open. I'm always happy to answer questions about this sort of stuff. This is my bio. It just says that I'm old. The most important point, really, I think, is the one on the bottom, which says I got into this really kind of almost by accident, by virtue of needing, when I started a user group, to have content. We couldn't get enough speakers. I'm not particularly like super smart. I just have done it enough times to have the confidence to stand up in front of you. But if you can get past those initial nerves, all of you have something to teach somebody else, all of you. I work on an open source project called Brighter. .NET devs in the room? A few of you? Yeah, so we compete with Mass Transit and Service Bus. We compete with Mediator as well. We have we can be used as an internal bus, similar to Mediator, as well as basically being external. And we're always very happy to work with folks who want to do OSS contributions and come and join us. We're a pretty friendly bunch. All right, what we're going to talk about. We're going to talk about an idea from Pat called fiefdoms. We're going to talk about another idea from Pat called collaborations, and later on, emissaries is the third of the set. And we'll talk a little bit in between about some ideas around messaging, resources and activities, and things that go together to make it all work. So in about 2007, Pat published a paper called Life Beyond Distributed Transactions. Pat had skin in the game for distributed transactions. He was the person that built Microsoft's distributed transaction controller. He was an advocate for basically how distributed transactions work. And he wrote this paper to say, what happens if we assume that we can't use distributed transactions anymore because they don't scale very well? Now, this paper predicts a number of things. It is one of the things that led to the creation of databases like Dynamo, Cosmos, and Cassandra. It also, without having the words for it, kind of predicts the rise of container environments and application-centric computing. We, nowadays, in the kind of more messaging space, tend to know it most famously for really being the thing that kind of pushed everyone towards the Outbox pattern. It doesn't explicitly tell you how to do the Outbox pattern, but it pushed everyone in that direction by talking about transactional messaging. We'll come to that. In 2020, Pat, on his blog, released basically a new document. And this document was really an update to some of the stuff in Life Beyond Distributed Transactions, and brought in material he previously only really talked about at conferences and not issued in a white paper. So we will be talking about autonomous computing in that paper as much as we talk about Life Beyond Distributed Transactions, because I want you to see Pat's current version of the thinking rather than the 2007 version of the thinking. Just for those of you that don't know, what is a distributed transaction? So a distributed transaction is one where we have multiple scopes in which a resource we want to lock lives. often and most commonly a database. So if I've got two relational data stores and they live in entirely different places on my, in the cloud or somewhere, if I want to basically have a transaction that says something like, I don't know, in this side I want to update the order history, and in this side I want to actually update the individual current order or something, then what I need to do is lock rows in both of these data stores. To do that, what I have to do is essentially send a message to both of those databases and say, can I lock these rows? And you respond saying, yep, you can lock those rows, or no, you can't lock those rows, somebody else has got them locked. Okay. And I'll take a lock for you, right? A tentative lock for you. Ooh. And then depending on what happens, if everybody says, yep, we can lock those rows, we say, great, make this change now to the data, all of you, and tell me when you're done. Right? If someone says, I can't, then we abort and we say, okay, free all the resources, we couldn't create a transaction at this time. And then you might try again. Okay. 2PC is quite expensive because you tie up resources for quite a period of time across your network. But more than that, 2PC's problem is that you tend to effectively have to have a single vendor who has implemented a given protocol that everybody essentially is using. And if you start using different data stores, or you want to lock resources in a data store and a message queue, your problem is quite often you just don't have the ability to do that. And Pat's perspective was when he went outside and looked in the real world, people were just not using 2PC to solve problems. So the question he asked is, well, how do you build systems if you can't use 2PC to solve your problems? All right, so let's introduce the concept of a fiefdom. So basically think of these purplish hexagons as a fiefdom. What is a fiefdom? So a fiefdom is basically an autonomous component that has data which it hides from people outside, and an API at its surface area which allows it to communicate with the outside world. We can think of the data inside our fiefdom as what Pat calls inside data. It is private, it belongs to us. Nobody else is allowed to take a lock on any of the rows of data in our data store. Right? We can have two-phase commit, transactions, etc. inside that scope, but nobody else outside can. On the other side, basically, where our data leaves our service by virtue of our API, we have what we call outside data. I raise an event saying there's been an order purchase, and it has details of the order, right? That's outside data. You can capture that data. I published it. It probably doesn't have, hopefully doesn't have the same schema as inside, so I can change them independently. But it's necessary coupling. I have to let you basically couple to the schema of my API, right? I produced that event. You could cache that, right? You can cache it and you can use it yourself basically to answer queries or questions locally to wherever you are. So that's outside data. Now, you may say, well, fiefdoms sound a lot like microservices in, and you'd be right, but they're more than that. Okay? So your app running on a phone or your app running in a web browser is also a fiefdom. Has a boundary, it has data inside which you can't get to from outside, it has some kind of API to talk to it. So we think of both of them as fiefdoms in this model. The little guy with the hat is what we call an emissary. So talking to your fiefdom might be complicated. It might involve me in a series of interactions. That series of interactions is what we call a collaboration, which is the little stack of papers there. So in order to help us perform that collaboration, we may have some code which runs basically in the other fiefdom, which helps you interact with our fiefdom. The most common example of this is a user interface. Right? I want you to fill in some data and pass it to me in order to I want you to give me the details of your basket so that I can effectively turn that into an order along with your payment details and your delivery address, right? That's essentially the collaboration data that I need to send. How do I collect that data? Well, probably I've got a user interface where you type it in. And in order to facilitate you gathering that data, your emissary may need to use some reference data, which effectively is things like, what's your product catalog? So I can basically display that to the user, and the user can pick from a list and choose the things they want, and then they send that back over to me. But an emissary could also be something like an SDK, right? It could be that I've given you an SDK to help you use my service, and you another back-end fiefdom, excuse me, and you're running basically the back-end, and we've got a little SDK which helps you use my reference data and make reasonable requests to me across the wire, right? Make sense? Okay. So let's talk a little bit more about this idea of collaboration. It's work that we are essentially trying to do across fiefdoms. So you can see on the right-hand side, fiefdom A. And fiefdom A essentially says, oh, some work has begun. We'll come back to how that might start in a second. It does some work, and it needs to call fiefdom B to get its work, get a response to some operation it needs before it can complete. So, for example, it's processing a customer's order, and it needs basically to see that the customer it needs to take payment from the customer, right? So it calls our payment service and says, hey, payment service, can you take a payment on the customer's card? And when you've taken that, can you let me know that that payment is done? And that's effectively a very simple collaboration between two fiefdoms. Okay. And we think about this as being a conversation or a dialogue because it has request and reply inside it. And there's uncertainty here. Right. When I ask you to take a payment, I don't know whether that's going to succeed. And there are a lot of reasons why it might not succeed. Some of them may be technical, right? Payment service may be down because someone's just basically balked it in some way with a bad release, right? It may be that your card gets declined, right? No purchases for you, my friend. Your card has been declined. And we need to manage that problem. And that is effectively what we lose a little bit in the post-world of TPC, things like transactional integrity, right? Is there stock for this before I can complete this? And so what Pat says is it's your application code that handles all of this. Right? Your application code running inside fiefdom A has to, through business logic, cope with the uncertainty of the transactions that are occurring. Later on, we'll see that really what we're talking about here is some kind of orchestration, right, that we are conducting around basically running a workflow where we say this has a number of steps and a number of processes that we need to complete. And this collaboration is by messaging between two fiefdoms. Why messaging? The problem is that if we try and use a synchronous communication protocol, the implication is that I'm effectively holding open a transaction in my service to you while you complete some work and respond back to me. So in essence, although I am not explicitly using two-phase commit, what I'm trying to do is emulate that model. Even if, in my code, I stick some async on basically the call that I'm making for you and say, hey, see, look, I'm asynchronous. The reality is, that's a problematic sort of asynchronous because if your app goes down and restarts, no one's receiving that call back or whatever, right? So what we want is something a bit more resilient, which messaging gives us. And messaging basically says, I can basically do something else while effectively I send you something. So I am not locking myself into a transaction between these two fiefdoms. So you guys have Costa. What coffee shops do you have? Has the Costa Empire reached Lithuania? No. Okay. So Costa is a UK coffee chain. I don't like drinking in Costa. And the reason I don't like drinking in Costa is when I arrive at Costa, I go to the cashier and I order my drink. And the cashier stands there. Either she is the barista or sometimes basically she and her mate, there's two of them working there. And we wait while my coffee is made. When my coffee has been made, then I pay for it. Behind you, there is usually a queue that's building up and beginning to extend out of the door. And people at the end of the queue are getting frustrated and they are walking off, going, huh, in the morning as they disappear without their coffee, right? The problem is that there's effectively a synchronous interaction between the barista and the cashier, right? One is waiting for the other. I issue the instruction for the coffee to be made. I wait for the response and I block. And the queue forms basically behind. Nobody can do anything else right now apart from standing alone waiting for their coffee, and you will lose orders. Starbucks doesn't do that. What Starbucks does is basically I go to the person on the counter and I say, here's my coffee order, and they write it on a cup. They write basically what I want, and they write my name. The name's quite important. The name is a correlation ID. It enables me to retrieve my coffee when the barista has made it. And they put it in a queue for the barista. They queue up the cups. They basically use messaging to send a message to the barista saying, please make this coffee. It's in the queue. When you get to it, you'll find the instruction written on it for how to make it. At the other end, a customer will pick it up and retrieve it. I can do other things while I'm, hanging out, waiting, but etc. But because I've committed to making a coffee, I like to run away, right? And so basically, Starbucks uses this messaging-based model. That's why they don't care what you say, what your name is, by the way, as long as it's not the same as everybody else. So you can do the whole thing and say, my name is Spartacus, and everyone can shout, I'm Spartacus, no, I'm Spartacus, right? You can pull that gag. They're not really worried. What they want to do is just make sure that they can re-tie up customer and message. And that's why we use correlation IDs. We'll come back to that a bit later. Okay. All right. So our collaboration needs to store some state usually. So what happens quite often is we have a thing called an activity for Pat. And an activity begins when our fiefdom, something initiates work, right? It may be a message received from another fiefdom. It may be a request on an API we expose. It may be time has elapsed and a pop has gone off on a timer to tell us to do something. But we've begun an activity. And we proceed with our activity, whatever our code does, processing the customer order or whatever, etc., until we reach a point where we need to call somebody else. Right? And what happens is we basically set up something in our, we set up some state, which basically says, I am currently doing this activity. And then essentially, when I have to do some sort of call to another collaborator, I can kind of say, well, this is the point I am at. I can move on and do something else because I'm waiting for a response on that one. But the activity can also basically help us recover because it says, well, we can retry operations, we can look at timeouts, and it can even basically store state that allows us to basically crash and come back up and say, what were we in the middle of doing? Or another, it allows another service to pop up, replica set pops it up another instance and says, okay, where were we on these? It looks like this one's not completed or finished. So our activity governs both our own work, our own response to receiving a request, and also manages our interaction with other fiefdoms in the sense of saying, hey, I want to communicate with another fiefdom to get work done. I need to get the payments information out to this other guy in order to get the orders processed. And one of the things we store is this idea of I've sent you a message or I've received a message. So you say, well, I need to send a message out. So I'm going to store that I've sent that because that might help me later if I need to, resend it. We'll look at that later in Outbox, inbox. Or I might say, oh, I've received a message, right? So what happens is I build up a history of the communication that I am involved with as part of the activity that I am working on. Now, it's quite possible that in response to me calling you, you will call somebody else. So I have an interaction with you where I say, please go and do this work for me, right? And you say, great, I've got that. Actually, you know what? I need to do some work. I'd call somebody else to get my part of the work done. And these things can spread, right? But notice what there isn't is a kind of centralized controller who's aware of all the steps. Each person just knows how I interact with the others in order to get work done. What you do to facilitate my request to accept payments is entirely up to you, and that may involve you initiating conversations yourself. All I need to know about is I need to call you and get you to do payments. So we have to have this correlation ID. We mentioned that in the context of Starbucks. Typically, basically, we're saying, well, let's put it in the message of the headers of the message, which says basically, hey, this relates to this. So when I send it out to you, you basically say, great, I've got your message in the inbox. Here's the correlation ID. When you give me a response, you give me the correlation ID back, and I know basically which it's for. Typically what's happened is I've saved some state into my state machine, into a data store saying, order 123 is currently in the status, awaiting payment, right? And then what happens over this side, effectively, is I take the payment details. I maybe have to call my payment provider. Eventually, it comes back, and I say, "Hey, payment 123 has been made." And effectively, that comes back in, and I go, "Okay, I've got a response back. This is the correlation ID. I will go and look up the relevant data in my data store for this activity, and I will then say, okay, what state's it in? Awaiting payment. I'm a payment. I can move it on to the next stage, right?" And so I'm managing this state machine for my part of the activity as part of this process. Okay. When we want to think about the fact that we might be part of a bigger piece of work, where essentially it's not just about my interaction with you, but the interaction has to move beyond that, we may also want to think about an idea called a conversation ID, which says we have a kind of correlation ID that relates to our request-response interaction between the two of us, but actually, this thing may go all over the shop and may help diagnostically for someone to basically be able to figure out it's part of a larger conversation about, for example, this order. Typically, conversations are more common we find natural IDs because there is some work involved which basically has some user outcome. But typically, correlation IDs are often just things like GUIDs. But you could use a GUID for the conversation ID if nothing else pops out at you. The other thing basically is that a collaboration, which we referred to earlier, essentially is where we have this conversation ongoing, right? And it's any situation where we have a requested reply with basically, it's actually that should say at least one partner. Okay. And the collaboration itself, though, is the workflow to get some work done that occurs across all of the participants. So the collaboration takes the conversation ID as its identifier. So we can say that an activity provides orchestration. Now, so that those that don't know, we tend to distinguish in messaging land between two ideas, orchestration and choreography. Okay. So orchestration is when essentially you have a conductor. Somebody is telling everybody where to go and what to do next. Choreography is where we essentially agree the steps of the dance beforehand, but there is nobody directing when the performance is happening. Okay. So here, each fiefdom acts as an orchestrator for interactions with its collaborators. Interestingly enough, the collaboration itself is choreography, because the series of steps have to be pre-agreed, and no one directs all the possible little flows that we have between the various fiefdoms. Although each pair of interactions is an orchestration, then what happens effectively is the overall flow, the collaboration may well be orchestration, because the fact that I call you and you call somebody else is just a pre-agreed dance. It's important for those of you that understand that orchestration is effectively what a saga does, to understand in this model we are not effectively doing sagas. Typically with sagas, what we have is some kind of externalized process manager. And that process manager essentially coordinates activity across a number of services. We don't want to do that. And the reason we don't want to do that is essentially we create this kind of God component that sits over here that has all the business logic and the workflow logic and a whole lot of dumb services that essentially pretty much just abstract a data store where data gets written. Right? It's called the entity service anti-pan. We want our individual fiefdoms to own their domain. So we want them to own the workflow that is part of the domain. And the bit of the workflow they own is the bit that they know about and can make assertions about. I do this work, and as I do this work, I need to talk to you to do your bit of the work. I can make assertions about that, I own that. I don't know how you do your work, but that's okay. I send you a message, I record the fact that I sent you a message, and I receive a reply, and I record the fact that I received a reply. I have a history of what I did as part of basically this process. You have your history, that's fine, and you may have done things with other people. But we do not need an externalized process manager running a saga in order to get transactions to successfully complete. The orchestration runs instead inside the fiefdom, and it's only about, this fiefdom doesn't run everything. I only know about my collaborators. So I don't know that fiefdom C is involved from fiefdom A, right? I don't manage basically that interaction. What I manage basically is my interaction with fiefdom B. Mentioned that. Okay. All right. Cool. And this is important because of causality. Right? So one of the models we see occasionally people fall in the trap of with messaging is I should be raising events everywhere. Events are loosely coupled. What happens is in some kind of pub-sub model, I say there are 0 or more possible consumers for my event, and I just broadcast events, right? I don't send something and get to a given participant and ask for a reply. The problem with that is many things effectively require causality. I don't want to ship you the order until you've paid for it. I don't want to sell you the order unless I know that we have the item in stock. In order to do that, we have to essentially have a request-reply interaction between two fiefdoms. I send you a message, you give me a response. In return to that response, I will do something, right? I'm not going to ship you the order prior to getting the notification back that you've paid for it successfully. Otherwise, I'm going to have a huge problem with every failing order. I then have to try and chase it with some kind of cancel message to say, no, but cancel that one, he didn't pay, right? So there has to be cause and effect quite often. And in any situation where you have cause and effect, you are effectively sending somebody a message, transferring them control of the workflow, and saying, I need you to do your activity at this point. Okay. Collaborations also, of course, have unhappy paths, right? It may be that your credit card is declined or whatever. It is simply another path that we have in our domain logic, right? Our workflow logic has to cope with the idea that there could be failure and take appropriate action as a response to that. We can also manage tentative operations, very similar to the way that TPC does, in the sense that I can say to you, okay, I need you to reserve the stock, seats in a cinema, tickets for a concert, airline tickets, because the customer is engaging in trying to purchase them. So I send you a message and say, please reserve this. You may have a timer, as fiefdom B, saying, I'll reserve it for a limited window of time. If you don't complete your transaction, I will free up the resource to somebody else, right? And in response to basically you saying, yep, I've given you a reservation, I will then go and do some work. And if effectively at the end of that work, customers paid or whatever, et cetera, that kind of thing, I will then commit to say, okay, yeah, cross off that resource that's limited in capacity. I've now taken that. I commit. So we can do the same kind of model, basically, that TPC tends to encourage, where we effectively say, hey, reserve something. When I get a response back, effectively, you can reserve me one of those for me. I can do the work required to complete the transaction and tell you that that is now done, right? So these are tentative operations, and they are quite common in collaborations between fiefdoms. Okay. And of course, a tentative operation might roll back. In other words, customer doesn't have the credit for it. Customer decided they didn't really want the tickets after all because they couldn't get the seat they wanted. And essentially, if I know that because the customer exits out, I can effectively roll that back and tell you, free up that a resource for somebody else. So that's the key thing with this microservices argument about smart endpoints and dumb pipes that I want to try and reemphasize again is that effectively, although this may look like a saga or something like that, right? There is no externalized manager. Right? Your activity inside your fiefdom is driving your portion of the workflow, and all you do is send messages to other people to get them to execute their parts of the workflow. All right. When we think about basically the two types of those came in my talk the other day, we distinguish between messaging and eventing, or commands and events, if you like. Messaging is basically a conversation about the future, right? If I send you a message, it's basically proposing to you that the world should look like this. So a lot of interaction in fiefdom is me transferring control to you, right? And saying, I need you to take a payment. That's a conversation about the future. There is no payment right now. I'm asking you to bring into being a state of the world where a payment has been made and respond to me. Okay? Eventing is a conversation about the past, right? You say something happened and I want to tell you about it. The payment was successfully made. Here's basically the answer to that question, right? And these two things need to be understood as distinct, right? If I want you to do something and I know it's you doing it as opposed to somebody else, that is, I'm sending you, I'm using messaging, right? If you want to tell me about something that happened, you're using eventing. Okay. So it's immutable, stale, and versioned if it's an event. In other words, there's no point in you trying to change it because it's done, right? It's stale because facts may actually have changed in the fiefdom since the point that you received it, and typically it's versioned, all right? Hey, this was version 14 of basically that update, just in case anyone asks you which one, because there may be a later one. All right. And that is how we build reference data and event carried state transfer. So looking at basically this diagram from fiefdom B essentially what happens is for some reason changes some inside data, right? Customer address is updated, customer phone number changes, details of the warehouse location change, stock in the warehouse changes. Right? And what I do is I publish an event to say something has changed, which you downstream may care about knowing about. Okay. It is historical past state. You save that locally to you and the other fiefdom. It's outside data, so it's fine. It's a copy of some information you're sending to me, right? And I can use that reference data as a lookup if I want to know, hey, what's the stock levels like? I don't have to make a GET request to you. One of the things we don't want to do as much as possible in any kind of modern microservices architecture is make GET requests, right? It's a synchronous call. I'm effectively dependent on your uptime. I'm having to get data effectively. I may have to do it repeatedly, right? What I really want you to do is give me the data in advance so that I can actually answer those questions myself. And we understand this implicitly in the sense that when we build web-based clients, we tend to cache a lot of stuff locally down on the client, so it doesn't have to keep basically making GET requests back to the server to do stuff, right? But that's actually very true between services too. Services, we don't typically want to say to them, what's the stock level right now? Just let it tell you what the stock level is when it changes and listen for the information. And that helps us build up this thing called basically reference data, and typically the mechanism used is what we call event carried state transfer. Okay. And it gets stale, so we need to keep pumping changes, right? So what happens is effectively you keep pumping changes saying, hey, my product catalog's changed. Hey, the customer details have changed. And effectively I subscribe to those changes in the same way Pat's sort of model was, once upon a time when he was a kid, he used to get a mail order catalog come through the door and they'd all pour over and order stuff basically from the mail order catalog. And you subscribe to the catalog and every month you get a new catalog telling you what was now available. Reference is very much the same model, right? I subscribe, you keep telling me what the updates to the catalog are, I've got a copy of the catalog, I can make orders now. Okay. So the emissary over in fiefdom A, a little stick figure, he's application code that typically, quite often in a modern world, we would ask the people in fiefdom B quite often to write. That runs basically in this other fiefdom, which may be another microservice, but it could be a web app, or it could be a micro front end, right? Or it could be a part of effectively our phone app. And typically what happens is the emissary uses reference data, it's been published. So I have some data local to the client, which enables me to successfully make requests. In other words, reference data could be as simple in this case as, I'm rendering a page and giving it to you with some choices on it. That is effectively reference data that I've given you, right? Because you have a copy of the data which enables you to make selections. The emissary is your UI. You pick stuff off it, and then you make choices, and effectively that results in you calling my API to get work done. So the simple example basically is UI code. But more complex examples, basically, your SDKs, where effectively I have a complex interaction with you. In the current job, we have at least one of those where we have an SDK that's shipped with the reference data, so you can use the reference data more easily. We don't ever trust emissaries, right? They're not inside our trust boundary. They have no privileged access to anything inside. They can't reach into inside data. They use our APIs like everybody else does. We may have written them, but we still don't trust them. Therefore, we always validate their input. Okay. And typically, one of the things Pat says is, consider your emissary to be offline. What does he mean by that? When we build offline user interfaces, one of the things or things that are probably not permanently offline, but are often disconnected, right? Typically, the model might be, hey, I know that you could be offline, you're going to go and do some work, and you're going to hit a button to kind of sync your changes up to the server, right? And he says you should really build all UIs that way. Think about giving them all the data they need to render stuff, et cetera, and make choices via reference data. Let the user go and do work locally, and at the end of it, they hit a button basically marked, send stuff back to me at the top to basically execute something on my behalf. And in theory, you could queue that. Although a web app, you wouldn't, but effectively, in theory, you could queue those up when you actually were connected again, right? So the idea is to allow your client to be as independent of this fiefdom as possible of having to interact with you all the time. Don't keep making GET requests. Make some at the beginning, load up the pages, get all the data down that you need, let the user interact with it, and when they're done their work, let them hit a button and send you a message. Okay. All right. In order for some of this to work, when I send you a message in response to a change to either an activity or a resource, so a resource is just something that you care about, like stock, orders, whatever it is you're tracking, the entities basically you care about. Oops. Then what I'm going to need to do is make sure that in order for me to change my local state, right, of that resource, I have put a message on the queue. And that implies a transaction, right? It implies a transaction between my queue and the entity. But we know that would have to be a TPC transaction. Pat's already pointed out to us those are difficult because we may come from different vendors. So what do we do? How do I effectively make sure that I have consistency such that when I make those internal changes that I need to signal you should now take some operation, how do I make sure those two things are happening together? And the most basic answer we have today is called the Outbox pattern. So that says basically, alongside in my data storage, the storage for my resources, for my entities, I have a table called an Outbox. And in there, I write the message that I want to send. So I can create a transaction that spans those two tables. I write the change to the entity, and I write the message I want to send. Then an out-of-process component can pick up that message and put it on the queue. I can look for messages that haven't been sent and send them. And I can keep retrying that until basically it happens. That's called guaranteed delivery. Okay. I will keep retrying it until it happens to make sure that we eventually become consistent. You can, in many cases, with frameworks that support this, do an immediate send as well, where effectively we write them both, and then we immediately try and put it on the queue to reduce the latency of waiting for the worker to poll in the background. Typically, you try it once or twice, then you give up, because you then let basically the sweeper process finally make sure that you actually get guaranteed delivery. Okay. You can't know for sure if the fact that basically the line in your Outbox table saying when was the message sent, so you know you don't have to send it anymore, wasn't updated because you didn't send it, or because the right back to the database to tell you it was sent failed. You know, you failed to basically get that row locked and you can't write to it, or maybe the broker doesn't correctly signal that it has sent it. So you have to anticipate duplicates. So I refer to it as guaranteed at least once in messaging, right? It's at least once because I may send it to you twice, or 3 times, or 4 times. It's the only way I can guarantee. And it's a distributed systems problem. There's no way around it, right? So what everybody does is they have an inbox. So they say, well, what I need to record is messages I have seen. And then if I've seen this message already, I know not to basically act upon it. Interestingly enough, as you can begin to see, when we talked about activities, we said one of the things activities record is messages they've sent and messages they've received. So outboxes and inboxes become part of your activity code because essentially what they're doing is recording the interaction you're having with other fiefdoms. You do have an option which is idempotence, which is to basically say, I don't need an inbox if just reapplying this message will always result in the same outcome. Right? Sometimes, what you may want to consider doing is putting your inbox in the place where effectively you say, if I receive a message I've already seen, even though I won't run my application code to change my internal state because deploying it twice would be bad in my case, I may choose to resend the message that I would have sent as a result of that action, which lives in my outbox. I can do that by clearing the delivered tag, right? In case the reason the person upstream sent it was someone downstream said, well, we never saw that. And what they're trying to do is flush the messages all down the chain to try and recreate something. Right? So you may want to do basically to guarantee your response. All right. Some DBs don't support transactions effectively across your database, right? What do you do about that? Typically, most of them let you do a thing called log tailing. They let you listen to a transaction log in that case, which effectively tells you about all the writes that are made to the system. Typically, what you do is you listen to that transaction log, and then you write an entry into the outbox for each transaction that was written, and then poll the outbox as before. Okay. Now, the cheap option is called state change capture, and that's when I put the message onto the wire, onto the queue, before updating even my local state, and I update my local state from the message. So if there's a message, everybody eventually writes the information to their local store when they give up processing the message and say, we're now up to date. Only downside is you can get strange effects where somebody downstream has written the result before the upstream person has, right? So you can get timing issues. Just watch for that. But it's the simple option if you don't want to do the outbox pattern. All right. So Pat's point about how this all works is that the implementation to some extent is up to you, right? It's just code. Here typically would be a model where we say, I've got some collaboration, and that collaboration really is a result of messages being sent to and from my app. Command messages coming in and probably events coming out from me as a response to those commands. Typically, I have 2 things within my application: a resource, a thing that about our domain we want to track the state of, and an activity, any state we want to have where effectively we need to, for some temporary period of time, pause whatever we're doing and be able to recover to get back to it. And typically, your application code drives both your response to a command, creating an activity, updating any resources, or waiting for basically a reply to come in, and refreshing it and pulling it up. All right. Briefly, I will show you some code. So Bright, which I work on, I gave a talk at the .NET User Group the other night, which gave a little bit longer about this. But this is just an example of how you can do it with something like Brighter, right? So typically what you do is you write handlers, and those handlers essentially are how you respond to messages coming in on a queue, for example, or a stream. That attribute there says we're using an inbox, and what that just means is we have a middleware pipeline, and we're saying, hey, look for duplicate entries. And the idea here is I've got a handler which says, at some point, I've been asked to do a checkout. And this is probably being driven by an internal bit of code that's basically called the handler. And what we're saying is, well, what we want to do in this is basically create an order and send a message to another fiefdom, which is going to take the payment. So I'm going to begin a transaction to make sure I can write to both my Outbox and to my resource. Then I'm going to create my new order, and I'm based on the checkout information from the customer. I'm going to validate that's actually correct, and then I will write the new order to the database, right? So I've created an order for the customer. I'm now going to create a payment request, right? And I'm going to basically put into my Outbox that payment request. Probably when I do my create order, I'm creating in a state like, you know, awaiting payment or whatever, somewhere in there, so I will be able to manage that state machine. And then if everything's successful, I commit the transaction, which basically puts the message into the Outbox and basically puts the new order into my data store. Okay. Or if it was to fail, I would simply roll back. And then effectively, when I get a response saying there's a payment, again, I'm using my inbox to make sure I dedupe. Receiving a payment's probably one I could treat as idempotent. It wouldn't matter if I paid for something twice. And then I say basically, okay, I'm going to handle the payment message you sent me, accept payments fiefdom. Again, I'm going to begin a transaction because I want to send a further message after updated state. I go and look for that order, right? I do a search for the order in my database and say, this payment must be for an order. That's basically what I'm using as the correlation ID here. I'm going to go and look up that order. And when I get that order out, what I'm going to do is basically update it to say that the payment's been made. I can then create a new message to say, well, we can fulfill this order now. I'm going to send it to another fiefdom, put it in my Outbox, right, and then commit. And that kind of code is effectively what an activity is, right? And that's kind of how you build these systems, because I don't need an external orchestrator. I just need to send and receive events and react to them. All right. That's me. A little bit over time. Sorry about that. I think we are the last talk in here, but you probably got other things to go to. Does anyone have any burning questions at this point?
How do you visualize the...
Hang on, I've got the mic, which is a bit of a problem.
How do you visualize the flow and then debug it if something happens?
Okay, that's a good question. So you have to get used to the idea that it is difficult now to debug the flow because you've got them in multiple independent processes. You're basically much more reliant now on tracing. So really you want to use something like OpenTelemetry, et cetera, and be able to trace the span so you can see the flow through tracing. Debugging is not that easy, for sure. Any other questions? I'll be around at the conference this afternoon after this. I'm probably going to get coffee from wherever the coffee thing is. Feel free to just wander up to me and ask me questions. I am here for you to talk to at any point, right? I'm not having to do the day job. So feel free to come and basically just walk up to me and go, hey, Ian, I wanted to ask about X. I promise I don't bite. All right, thanks so much, everybody.